In this video, let's check how to source smoke from an object or particles. Also, how to guide smoke with custom velocity actually derived from particles. So let's drop down a sphere. This will act as a source for smoke. And next we go to the pyro shelf, and as we use below is smoke, you have to click here, and with this it has created a simple smoke simulation for us. Let's play the simulation. Also, we can find in the network editor that all the necessary nodes have been created for us with default settings. Now as we dive inside the top network, we will find the network which is very similar to what we used to have in the previous versions of Houdini. I'm showing this tutorial in Houdini 17.5. Now this import node is actually showing density imported from DOP network. But when we dive inside the object node network that's used as a source, we are here in for a surprise. By default, the network here is different from what we used to have in the versions before Houdini 17. In the previous versions, we used to create source volumes directly from the objects, be it density or velocity volume, whatever. Now first, Houdini has scattered particles or points on the surface of objects, and these points are then associated with attributes like density and temperature. Then these values are randomized and animated over time. As you can see from the spreadsheet, we play the timeline and these values are changing. When these points source smoke, the smoke evolves with varying density. Now here we click this icon and we can visualize the attributes as varying colors. Okay, finally, after the necessary attributes are in place, they are eventually converted to volumes. Well, in the previous versions, Houdini 16 and before that, when we created source volumes from a surface or a curve, or say we wanted to create velocity volume from an animated particles, a lot of times we had to struggle finding the right way to create the volumes from it. It was not that readily available, and we always used to derive a mechanism just to create it. But now this is the standard way. It's simple and they claim it's fast. First create points or particles, then create density or use its velocity to create volume. Then fetch the volumes using source volumes. You can see this inside this top network. Okay, so let's say instead of sourcing from the surface of object itself, we wish to source smoke from particles. So let's birth particles from the first context geometry. We will have 500 such particles per second. Some upward force is added. Some noise added as well. Now we will add this node called pop axis force. Let's increase its sphere of influence sufficiently large. And now as we increase the orbit force, we can see that the particles are evolving around an axis. In this case, around the y-axis. Now let's dive up, and we wish to use these particles as a source. So let's plug in the out into this network. Now inside pyro source, in this case, instead of using source smoke, instead of surface scatter, we will use keep input. So let's dive inside the top network and allow the simulation to play. Yeah, the particles are emanating smoke. Now just for better display, we can add light by rotating our camera to the direction we wish the light to come from, and control click to add light. Now as you can see, this has given a better 3D display. The light is coming from a side and we have shadow on the other side. Okay, so instead of flat looking smoke, we have an interesting smoke display, and this smoke is sourced from the particles as intended, achieved without much of a hassle. Now in this case, we wish to source smoke from an object, say torus, but velocity has to be derived from particles, from particle animation happening in a different chain. Now this is a simple particle simulation with an upward force applied, a small orbit force there as well, so the particles are revolving around y-axis. Let's move up one level and create the necessary structure for density volume. So scatter points on the surface, and here in this case we will use surface scatter and not keep input. As you can now, as you change the initialize method to source smoke, this would add density and temperature attributes. Add attribute noise over here, give the attributes density and temperature, which we wish to vary over time. So for this, click animated options. Now when we color visualize, we can see colors animating across time, so showing that the attributes are changing over time. Also we will add volume rasterize attribute to finally create volumes from these attributes, density and temperature. Now as we play with these values here, we can see we can achieve even harsher contrast. So density appears for some points and almost nothing for some points. So add a null specifying the end of change here and name it out density. So when we fetch it through source volume, it will be easier to locate it. Now if we look at this side, you can find all sort of attributes coming out of pop network. So let's delete them first. Add attribute delete, remove those attributes. Okay, but in the process the velocity attribute is also gone. We should have kept it, but it's fine. We can create velocity using trail. And from these options we choose compute velocity. So in geometry spreadsheet we have velocity available back. Now when we use pyro source node, it creates p scale attributes, very essential. So we need to add one on this side as well. Here I am creating a slider, chf my p scale, and I am pressing the button here to create the slider. Let's input a value of say 0.2 for p scale. Now let's create the volume for velocity, and the attribute here is v. Let's end this side of the chain with a null out velocity. Now that our volumes, density and velocity both are ready, let's create the top network. Most essential, pyro solver and smoke object, which acts as a body, or you can say a container where simulation happens. We are keeping our number of voxels counts low at the moment, which means the size for each voxel will be large. Means a low resolution for simulation, but for the sake of this tutorial, so that the simulation happens faster, let it be. We obviously have to create box size of we obviously have to increase box size of smoke object. And now fetch our volumes using volume source. The first one will be density, so torus object out density. Now density is scalar, source volume will density and target field will be density. Okay, let's duplicate this, and this time velocity is coming as v. The source path it's going out to be out well. I'm just making it like so. Let's merge these two together and plug this into the last input. We will dynamically resize the smoke object, so only the voxels where density appears come into play, and later as needed the smoke reaches outward, the voxels they are calculated. And the way to do this is through gas resize fluid dynamic node. So let's dive up and let's visualize data intensity density. Okay, we play the animation. I think we might have to scale up the velocity value, give it a value of say 5. Now play the animation, and yeah, as intended we have the density source from surface of torus and the velocity is being derived from particles. However, one thing you might have noticed, for some of the voxels density is there, but the particles animating might still be reaching there. So means density has appeared but no velocity to guide it. Might actually be much more happening inside Houdini, but we can assume this way. I can say this something like say these squares are voxels, and as density appears here in this voxel, we want the velocity value to be present there already, derived from moving particles, thus giving direction to velocity and the smoke to flow in the direction. So in a way we wish to have velocity values or velocity field present there even before the density appears. Let's see how we can achieve it. So let's prepare the velocity field, and this we will create from velocity derived from particles itself. So we'll have to freeze the movement of particles first, take time shift, scrub the timeline to find a proper frame. I think frame 75 is the right candidate. Now it's time to create an area to scatter points. Drop a box, resize it. Since we want the points scattered all over the volume of the box and not just the surface, first we create fog, and that way the points are scattered inside as well. Let's scatter 5000 pi points. Now these points will share the velocity values from particles coming from this side, and for this we will take an attribute walk. We will connect this to the first input, and this side we will connect to the second input. Let's drop a point cloud open node, connect point position to position and output 2 to file input. Now the way this point cloud system works is we will query the velocity value for a few points, point cloud that's been created around every point, average its value and copy that velocity value to the point using bind export node. Okay, let's jump out and we will see that we have velocities values associated with points now. No velocity. Okay, yeah, there we have. Now just in case we want to visualize the velocity values, we can generate such a visualization with a volume trail. Volume trail takes two input, the point with which you have the velocity. Now since this is going only for visualization, let's lower the points, say 500, and the other input requires velocity volume, so we will have to create a velocity volume. So add a volume, plug in the bounding area for volume. Now this volume this well volume has no values at present. We need to supply it with velocity values from particles. So let's drop down volume warp. This is very much similar to attribute warp, but it works with volumes. And in fact we can take these nodes, copy them and paste them inside the volume warp. Very handy. Okay, so connect these two and connect the output 2 with the file as well. Again we are querying the values for velocity and dive up. Now we make the necessary connections here, just like the way we had set up the attribute warp. Okay, connect this one, and this is not showing. How come? The reason is simple. We have to increase the number of points, so every point can find some particles to query velocity values. We are querying V. Okay, we wish to output well actually. So there we go. We now have a good way of visualizing how the velocity flows across the field, and I think we can increase search radius now. So the same settings we need to apply for attribute warp PC open also. Increase search radius and number of points. Alright, let's increase the number of scattered points again back to 5000. You remember we reduced it earlier since we wanted it for visualization purpose only. Also, the size of torus here, I think it's very small. Let's increase it somewhat. Also, one thing I would like to add, inside this attribute warp here, let's add some noise with the velocity. So let's add curl noise, and this noise with the velocity. And let's play with the frequency settings here. 0.8 will do. The rest, let's keep it as it is. Okay, we need to connect this with the bind export. Jump up a level and check our simulation. Oh fine, this is working. Yeah, remember we had kept the resolution everywhere very low, but this was just for the sake of this tutorial, since we wanted the simulation to happen fast. Carrying the same concept forward, now we would like to give direction to the slope using a curve. So now let's dive inside this curve object, and this is the setup that I have already created. And what exactly we have done here is, this is the curve. This is responsible for giving the direction. We are creating basically normals here, and the normals are going to be the velocity source for the velocity volume, whereas this sphere here, this is going to be source of our density. So let's check what exactly we have done here. This is the curve, and all we have done here is given it normals. If you want to visualize the normals, all you have to do is just select it and press X, and this is the vector value. The attribute we have provided is we want to visualize as normals, and as you can see, the normals are going downwards, but what we want is the normals to be reversed. We have given it a simple X expression. to reverse the normals, and now these normals are going to be let me visualize this thing as well. So these normals are then going to be the source of velocity volume. So first we have the region where the volume exists, and then we have created the necessary volume. This is going to be fog volume, and let's scatter some points inside it. The normals from here, I need to somehow provide that information to these scatter points, and the way we do so is again through PC open node. This is similar to what we have done earlier as well. The normals are coming from output 2. Yeah, the normals are coming from here, and we are querying normals, but then we are adding a little bit of curl to it. This is a vector attribute. All we are doing is now outputting it as a velocity attribute. So once we have points with velocity values, all we have done is appended a Pyro source node to it. So this has created velocities. We might have appended p-scale values to it as well, and then simply created a volume from it. Now this side of the chain is again a simple setup. We have the sphere here. We have created the necessary density and temperature attributes, added a little bit of noise, and finally converted it into volumes. Let's dive up, and as you can see, the curves normals are now giving direction to the smoke. Okay, thank you.